Hello everyone. In this video I'm going to give some more explanation about the theoretical part of the assignment number 2 and probably even give you some hints of how to do it. So let's start talking about regression analysis. Imagine the following scenario. Imagine that you are given some information about some students, let's say 5 students, about their height, and their weight. So let's say one of the students is 1.5 meters and we have 70 kilos, we have 75 kilos, we have 80, 85, and this first student is approximately 70, not exactly 70, 1.6, 1.7, 1.8, and 1.9. This student is approximately, not exactly 75, but is something around 75. Not quite. This student 1.7, so is a bit more than 80, something closer to 85. The next one is, for some reason, this guy is taller, but it's thinner than the previous guy or girl. And this student, something closer to 85, not exactly. So question: how to predict the height of a student who is 2 meters tall? How to predict the height of a student who is 2 meters tall? Well, intuitively, what you want to do is you would like to be able to trace a line, and then using this line to find out or an approximate value for his height. It's just an estimation, so we are just trying to estimate that the height would be something, this student would be this tall. So what we are doing here is a regression, which is a statistical model to estimate values for input variables, for input features, input features. So you try to predict an output or outcome variable. Outcome variable from a predictor or feature. Predictor or set of features. Predictor or feature. So this is what we are doing here, is a regression. The question is how to build such a line, because when we build this line, what we want is that this difference between this line that we design, the line could be, for example, here fx, something like fx. It's not exactly this, but let's say 75, so 40x plus 7. I don't know if it matches, but let's say you found out using regression that this is the line that defines the relationship between the height and the weight. So it means that the height is 40 times the weight is 40 times the height plus 7. Let's say, just an example. So using this function, what we have here is, sorry, this is blue. So this difference between our model, the predicted outcome, from the actual value for this student, this is an error, because we predicted the value, let's say 74.5, but the actual value is 73. For this guy, the error was bigger. So the model predicts something using this function. So this was predicted value, and this is the actual value. For here, we have a very close value. Here we have an error. Here we have an error. So let's say we have 1, 2, 3, 4, 5 points. So these are the points that we have. So the question is, we want to create such a line, this model, this regression model, where we minimize the errors. So this is what we are trying to achieve. We want to minimize the errors. And as you see in the course of machine learning, not just minimize the sum of errors. It's more interesting when you minimize the sum of the errors squared. So this is a better approach, and you see in the future course why this is a better approach. So this is just a context about where we use least squares. Least squares is just a measure. Least squares is just a measure how good or how bad your line, the line that you design, your line is. So if you have a line, a different line, let's say another green color here, and you have a different line. So this is an alternative model. If it's better or worse, I don't know. So let's see if it's better or worse. So then you calculate the error. In this case, the error is green. The error here, there is some error. The error is smaller. The error is almost the same. So it seems because of this point. Well, it's a hard call to say here on the eye, but probably let's suppose that the sum of the errors squared for the green line is smaller than the red line. So it means that the green model, this function fx 38x plus 6, let's say. So it means that this function better fits the data, better describe the data, the relationship between the outcome and the predictors and the input features. So this is the context of your assignment. Now let's talk about the dynamic programming part, the assignment per se, dynamic programming. How to use dynamic programming to solve this problem. I hope I wrote correctly here, so you can fix it. Dynamic programming. I think I misspelled something here wrong, but it doesn't matter at the moment. So how can we use dynamic programming to solve this problem? Let's compare here two scenarios. Let me compare here two scenarios. So let me clear my screen. I want to clear this screen. So let's see here two scenarios. What we want is create this line, not just one. Now we are allowed to create several lines. And as you will see in the PDF, we have one constraint that makes our lives easier, which is x1. We have all the points, so x1 is smaller. Now you don't have x1 or xi smaller or equal than xj. So all of them, x1 is smaller than x2, so on and so forth to xn. So we have x1, x2, all the way to xn. And then you have points here, one point, another 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 point. Okay. So scenario number one. What is the objective? We want to create not just one line. We don't want to create just one line. Not that we don't want. Probably is not the best option for this particular problem. But we are allowed to build several lines in such a way that we will minimize our objective. According to the text in the description of the assignment, you see it here. So we define a cost for this function that we are trying to create for these lines, not just one line. We can have, for example, one line connecting x1 to x3, then one line connecting x3 to x8, and x8 to x9. So let's say, so in this case we have 3 lines here. Why? Because these 3 lines have a certain cost. Cost for this line would be, in this case we have, because we have a line, so in this case we have, okay, 3 lines. The cost is number of lines, in this case number of lines, which in this case is 3, plus the sum of the least squares, the sum of the least squares. In this case we have this arrow plus this arrow plus this arrow plus this arrow. Why not the other point? Because there is no arrow here. The line connects this point, this point, this point, but the line doesn't touch this line, this point, and this point. So in this case we have an arrow here which will be computed and added here. Let's say this arrow is 0.5. Let's say this arrow here, this difference between the function that you predicted and the actual point is 0. Since almost the same, 0.4. And this one is, since bigger, let's say 1.0. So in this case the red line has a total arrow of 0.91949. But let's say instead of this line, what we have is one line connecting these 2 points, one line connecting this point, and one line connecting this point. So for this green line, the cost is again 3, because we have 3 lines. We could have 2, for example, but in this case, for some reason I chose the 3 points again. So we have 1, 2, 3 lines. So 3 plus the arrow here. Let's say here there is no arrow because the line connects 2 points. But here we have some arrow. This is 0.5 approximately. We have here some arrow here. Here the arrow was 0. Here we have some arrow since substantial 0.9. Here there's no arrow, and here we have a substantial arrow, let's say 2. So in this case we have 1.4, 3.4.4, 6.4. So in this case this function seems to be better than the red function. The red approximation seems better than the green approximation. So this is what we are trying to minimize. We are trying to minimize this cost function where we have the minimum number of lines and also the minimum sum of squared arrows. How to use dynamic programming here? So this is a good question. How to use dynamic programming here? Let's see an example. Let's see where how we can use dynamic programming. So we have x1, x2, x3, x4, x5. So here we have the points. So supposing n equals to 5, so we are trying to find the minimal cost. This cost as defined here, as we defined before, the number of lines plus the sum of squares for these lines that we created. So we are trying to find the minimal cost of all the points up to 5. What is one possibility? One possibility is we create one line here and we don't know the solution. We don't know the solution for this one, for this part. So we are supposed that we have a solution from a minimal a solution which is the minimal costs until the point 4, and then we have the minimum 4 plus 1 line. So the solution here, the cost of 5, if we choose this point here, in this point here. So the minimum cost for 5 using 4 as an anchor here, as an intermediate point. So it's equals to 1 because it's plus 1 line, and the minimum cost of 4. But wait, where is the sum of squares here? What is the sum of squares from 4 to 5? There's a notation here in the PDF. Let me see here the notation. PDF E I J. So let me erase this one. E I, in this case is 4, in this case is 5. So the minimum cost of 5 in this case is 1 because it's one line that we created, plus the minimum cost of 4. So we suppose that we found this value, we know this value in its minimal, plus the sum of square errors from connecting 4 to 5, which is in this case 0 because the line, there's no the line cross the point x4 y4 and the point x5 y5. So the error here is 0. So you just need to find this value. How to find this value? So that you probably start to feel the feeling that to see the pattern of a dynamic programming problem and solution. But we just one last detail. We were very arbitrary here because we choose the point x4. Why we didn't choose this point x3, for example? This is a good question, and it should be considered in your answer, because we cannot just guess that the subproblem is of n is n minus 1. It could be n minus 2. We don't know. Probably this would be a best choice, using this point as a intermediate or anchor or subproblem that you are going to build n5 on it. So yeah, so this is one which is not a complex solution. It is very trivial, in fact, the choice for this intermediate point. So should you use x4, x3, for example? Let's say we choose x3 just as an example. So n equals to 5. Let's say x3 was better than x4. So in this case, minimal 5 equals to 1 line because you connected x5 to x3, plus minimal x3 plus the arrow, the sum of least squares of the line connecting 3 to 5. This, in this case, is not 0 because I can see here there is some narrow here, a distance between the point x4, y4 and the model, the line connecting x3 to x3, the point 3 to the point 5. So which was the best choice? So this is up to you how to model it. We are not very far from the solution here. This is it. So just before I finish, what about the algorithm? You have two options. One, it's using memoization. So dynamic programming plus memoization. So you have memoization. So you will have recursive calls. In this case, you will have the recursive calls plus one of the arguments will be a data structure. Save the solution, the partial solutions. Another possibility is using a bottom-up approach. So you start to approach. So you start to solve the smallest problems, and then you keep solving the biggest until you reach the value of n. So this is the bottom-up approach. So this is it. I hope it was useful. I hope I clarified the problem and didn't make it worse. So If you still have some questions, so don't hesitate, you can contact me. So bye everyone, take care.